If you thought the latest images from the James Webb Space Telescope were extraordinary, the observations coming from another European space mission offer a completely different way of looking at the cosmos. The Euclid Space Telescope was designed for something much bigger than taking beautiful pictures of individual stars or galaxies. Its purpose is to investigate the enormous structures that connect galaxies across the universe and, more importantly, to study the invisible forces influencing them. Launched by the European Space Agency in 2023, Euclid was sent toward the second Lagrange point, roughly 1.5 million kilometers from Earth. From there, it can survey enormous areas of the sky while maintaining enough detail to study individual galaxies. That combination is what makes Euclid so important. Instead of concentrating on one small target, the telescope is creating a giant cosmic survey. It is gradually building a three-dimensional picture of how galaxies are distributed through space and how that distribution has changed throughout cosmic history. And when astronomers began examining some of its early observations, they discovered far more than distant points of light. They found enormous collections of galaxies, previously hidden objects, faint structures, and clues about the invisible material that appears to control the architecture of the universe. One of the most remarkable early results came from a huge mosaic assembled from hundreds of individual observations. The region covered by the mosaic was hundreds of times larger than the apparent size of the full moon in our sky. Within that enormous field were millions of stars and galaxies. What makes this even more remarkable is that this was only a small portion of the survey Euclid is expected to complete. So the images released so far are not the final portrait of the universe. They are more like the first glimpse through a much larger window. When researchers zoom into these observations, the scale becomes difficult to comprehend. A single image can contain nearby stars, relatively close galaxies, distant galaxy clusters, and extremely faint objects whose light has traveled for billions of years. Every one of those objects represents a different moment in cosmic history. This allows scientists to study the universe not simply as it appears today, but as it looked at different stages of its development. One of the most interesting targets is the Perseus galaxy cluster. Located hundreds of millions of light-years away, this enormous collection contains thousands of galaxies. Behind and around the cluster are even more distant galaxies whose light passes through the cluster before reaching Earth. Euclid's observations have revealed hundreds of faint dwarf galaxies that had previously escaped detection. These small galaxies may seem insignificant compared with enormous spiral galaxies, but they can provide extremely valuable information. Dwarf galaxies are strongly influenced by their surrounding gravitational environment. Their locations, shapes, and motions can therefore help scientists understand how matter is distributed around them. And this leads to one of the central goals of the Euclid mission: dark matter. We cannot directly see dark matter. It does not shine like stars, and it does not appear in ordinary photographs. Yet its gravitational influence can be detected. Imagine looking at a distant galaxy whose light travels toward Earth. If a massive concentration of matter lies between that galaxy and us, gravity can slightly bend the path of the light. The result is a subtle distortion in the apparent shape of the distant galaxy. This phenomenon is known as gravitational lensing. Individually, these distortions can be incredibly small. But Euclid is designed to measure them across enormous numbers of galaxies. When those measurements are combined, scientists can create maps showing how invisible mass is distributed across huge regions of space. In effect, the telescope is trying to reconstruct part of the universe using the effects of something that cannot be photographed directly. And this changes the way we think about what we see in the night sky. The stars and galaxies visible to us may actually be only the luminous surface of a much larger structure. Dark matter appears to form enormous halos around galaxies and connects them through the cosmic web. Galaxies are not distributed randomly. On the largest scales, they gather along gigantic filaments separated by enormous regions containing comparatively few galaxies. These filaments can extend across hundreds of millions of light years. At their intersections, matter becomes concentrated and galaxy clusters can develop. The result resembles an enormous web spread across the universe. But this web is not made from ordinary threads. It is largely shaped by gravity and the distribution of matter, including the invisible dark matter that appears to provide much of the underlying structure. For a long time, scientists relied heavily on computer simulations to visualize this cosmic network. Euclid is now helping them compare those predictions with real observations covering enormous portions of the sky. That comparison could reveal where our models are accurate and where they begin to fail. Some of Euclid the hidden side of the cosmic web. The deeper scientists examine Euclid's observations, the more fascinating the universe becomes. What appears to be a simple collection of galaxies from a distance turns into an enormous network when viewed at the right scale. Galaxies gather in groups. Groups gather into clusters. Clusters connect through gigantic filaments. Between them lie enormous regions where relatively few galaxies exist. Together, these structures create what scientists call the cosmic web. But this web is not fixed. It is constantly evolving. Gravity pulls matter together while the expansion of the universe pushes the largest structures farther apart. The result is a cosmic competition that has been unfolding for billions of years. Euclid is helping astronomers measure this process with extraordinary precision. One of the most useful clues comes from the shapes of distant galaxies. When light travels across the universe, it can pass through regions containing large amounts of matter. The gravity of that matter slightly changes the path of the light. By the time the light reaches Earth, the original galaxy may appear stretched or distorted. The distortion can be extremely subtle. A human looking at one galaxy would probably never notice it. But when astronomers examine millions of galaxies together, those tiny differences become statistically meaningful. This technique allows researchers to estimate where invisible matter is located. In a sense, Euclid is creating a map of something that cannot be photographed. And that map can be compared with predictions from cosmological models. If the observed distribution of matter matches the predictions, scientists gain confidence in those models. If it does not, they have a mystery to investigate. This is particularly important because our current understanding of the universe depends on several major assumptions. We believe that ordinary matter makes up only a relatively small portion of the cosmos. A much larger amount appears to be dark matter. And another enormous component is associated with the accelerated expansion of the universe. These ingredients form the foundation of modern cosmology. Yet the physical nature of dark matter and dark energy remains unknown. That is an extraordinary situation. Scientists can describe how these mysterious components behave on enormous scales while still being unable to explain exactly what they are. Euclid could help change that. Its survey is large enough to test these ideas across a huge portion of the observable universe. And the larger the dataset becomes, the more difficult it becomes for unusual patterns to hide. This is why individual photographs are only part of the story. The real scientific power comes from combining thousands, millions, and eventually enormous numbers of observations. Imagine trying to understand a forest by studying one tree. You might learn about the tree. You could examine its leaves, branches, and bark. But you would not understand the structure of the forest. Euclid is taking the opposite approach. It is trying to understand the entire forest. The individual galaxies are important, but the relationships between them may be even more important. How far apart are they? How are they arranged? How does their distribution change with distance? How does the surrounding dark matter affect them? And how has all of this changed over billions of years? These questions can reveal the history of cosmic structure. They can also reveal where current theories begin to struggle. One particularly important measurement involves how galaxies cluster. The universe was not born with its current structure. Early on, matter was distributed much more smoothly. Tiny variations existed, but over enormous periods of time, gravity amplified those differences. Regions with slightly more matter attracted additional material. Those regions became denser. Eventually, stars and galaxies formed inside them. Over time, the cosmic web became more pronounced. Euclid can observe different stages of this process by looking at galaxies at different distances. The farther the galaxy, the older the light we receive. This gives astronomers something almost impossible to obtain in any other way. A view of cosmic history spread across a single survey. Nearby galaxies provide information about the more recent universe. Distant galaxies show earlier stages. Together, they form a kind of timeline written across space. And this timeline may contain clues about how quickly the universe developed its large-scale structure. That matters because even small differences between theory and observation can become significant when multiplied across billions of galaxies. Suppose a model predicts that structures should grow at one particular rate. If observations repeatedly show a slightly different rate, scientists have to investigate why. Perhaps the assumptions about dark matter need to change. Perhaps dark energy behaves differently from the simplest models. Perhaps gravity itself works differently on enormous scales. Or perhaps there is another explanation that has not yet been considered. This is where astronomy becomes more than simply observing distant objects. It becomes a test of fundamental physics. Every galaxy becomes another piece of evidence.